So we're going to talk about highway capacity and level of service. Now that we have studied the traffic flow relationships and their use in shock wave and queuing problems, we can turn our attention to one of the most commonly used analysis techniques in practice. This is a subject known as highway capacity and level of service analysis. The specific subjects we're going to look at in this class are discussed in sections 6.1 through 6.4 and section 6.7 in your textbook. We are limiting ourselves to the study of basic freeway segments. It's a very limited study of highway capacity. But this will give you an introduction to the procedures that you can later expand on your own to the other type of facilities by learning the specific details. The difference between facilities is in details, but the concepts you're going to learn it with this very limited analysis that we're going to do. Highway capacity and level of service allow us to answer questions such as: what is the quality of service provided by an existing facility during peak periods, and how much traffic increase can be tolerated? What types of roadway or transit facilities are needed to accommodate a given level of person or vehicle flow? Notice that here we have persons or vehicle flow, so it's not just limited to highways. What lane configurations are needed for various levels of average daily traffic on freeways or arterial roadways? And what highway designs and hence capacities are needed to serve a planned development? And how wide must the sidewalk on a street with high pedestrian activity be? And would the holding space at the street corners of signalized intersections be sufficient? So highway capacity, it's one of the most commonly used techniques that those of you who work in transportation will see. The highway capacity and level of service procedures are categorized or classified based on whether traffic interruptions result solely from the interactions among vehicles or if there are fixed elements that interrupt traffic flow. The first category includes uninterrupted flow facilities. These have no fixed elements, such as traffic signals, that are external to the traffic stream and may interrupt the traffic flow. In these type of facilities, the traffic flow conditions result from the interactions among vehicles in the traffic stream and between vehicles and the geometric and environmental characteristics of a roadway. So examples of these are freeways, and this is what we are going to study in the class, multi-lane highways, and two-lane highways. The second category includes what are known as interrupted flow facilities. These have fixed elements that may interrupt the traffic flow. Such elements include traffic signals, stop signs, and other type of control. These devices cause traffic to stop periodically or slow significantly, irrespective of how much traffic exists. And examples of these facilities are signalized intersections, unsignalized intersections, and urban streets. Capacity and level of service procedures are not limited to highway users. There are procedures to assess level of service for other road users, including procedures for transit, pedestrians, and bicycles. Like I mentioned before, in this class, we will see a brief introduction to the highway capacity procedures for freeway sections as an example of the procedures for uninterrupted flow facilities. Then in the last topic covered in the class, we will look at some aspects of signalized intersections, which is an interrupted flow facility. In particular, we will look at the estimation of cycle lengths without going into the details of the capacity and level of service procedures. We're going to use something from capacity analysis, though. We will only use one equation from those procedures that is used to estimate what is known as a saturation flow rate. And I will define what that saturation flow rate is later on. So we will touch on something of the highway capacity model, but we're not going to look into the specific details. For signalized intersection, that tends to be very detailed. And if you want to learn more about that, probably you should be taking 462 with Dr. Prevedors, which is on traffic engineering. And I think he goes into a lot more detail of signalized intersections in that class. For those of you who plan to be transportation engineers, that's probably one of the classes you want to take, or the planning class with Dr. Chen, or the payment class with myself. So these are the two type of things we're going to see, the facilities we're going to see, freeway sections, and basically just basic freeway segments is just one part of what we can do for freeways, and signalized intersections, and we're not going to even look at the level of service procedure. So let's start talking about uninterrupted flow on highways. More specifically, we're going to be looking at freeway facilities, like I mentioned, and I'm sure you all know, or you have a good idea of what a freeway is. But do you guys know what defines a freeway?
The speed that's allowable.
The speed is allowable. Usually, freeway facilities, you have higher speeds. That tells you that usually those are designed for relatively high standards. But you know, what I put in here has something to do with it. Facilities with complete access control. You cannot access a freeway by no other means than a freeway on ramps, or you cannot leave a freeway other than at off ramps, right? So there are no access from abutting roads. There are some sections where you have lateral roads, and you have those lateral roads have access to businesses. You cannot access the freeway directly from those roads. You have to go and look for the closest on ramp, and the same thing to leave. So access is limited to on ramps and off ramps, and what makes those unique is that you have only merging or diverging maneuvers, right? There's no crossing. There are no cross streets on freeways. So access control is one of the defining characteristics of freeways. In addition, there are no signals, right? So stop signs or yield signs on the freeways. You will find some of those on ramps and off ramps, but not on the main line of the freeway. The document that defines the capacity procedures is called the Highway Capacity Manual, or HCM, and it provides procedures for evaluating the level of service and capacity on basic freeway segments, among other things. In this class, we will stick with what your book says, which is for the 2016 version. Probably when you graduate or a few years later, you have to look at the latest version. So the idea is just to give you an idea of what the HCM does. And then you obviously will have to relearn what we learned in the class and probably learn a lot more details for other type of. This is the outline of what we're going to cover. We're going to talk about highway capacity. We need to define what that means, what level of service means. Then we're going to go over the procedure of how we're going to determine the level of service. Just a brief introduction for freeway. So this is what's coming in this lecture and probably next one. So although you will often hear me saying that the best way to estimate some variable is to actually do some measurements, from a practical point of view, it is often difficult to devote resources for data collection to estimate a speed density flow relationship for each specific highway segment under investigation. I want to emphasize that I'm not just talking about collecting the flow on a given day at a given time of the day. I'm talking about developing relationships like we have been seeing between flow, density, and speed. If you want to get those, you need to have a lot of information that is typically prohibited to do it for every single facility. So often we will need to rely on models developed from other facilities to estimate the traffic flow relationship. It's impossible to take measurements on a facility before that facility is built, right? So when we're doing the design of a new facility, we have to estimate those quantities, how the facility is going to perform. The designer must also anticipate the operational characteristics of the facility in order to make prudent geometric design decisions. So these 2 points are indicating that for facilities that have not been built, we need to estimate things. That's what the Highway Capacity Manual does for us. It provides estimates that are based on observations of existing facilities of similar type and practical methods of analysis and design that utilize these estimates. Those procedures have evolved and been codified over the years. In the United States, the Highway Capacity Manual is the standard reference for capacity analysis procedures. It is published by the Transportation Research Board and is produced by the Highway Capacity and Quality of Service Committee of the Transportation Research Board. They are responsible for this manual, and both the Federal Highway Administration and the National Cooperative Highway Research Program support the development of capacity analysis models and procedures through funded research. It comes in PDF forms, but also it comes with software. So there's something called the Highway Capacity Software And you can see here a screenshot from the 2000 version. And this gives you also an idea of all the things that the highway capacity manual covers. Let's go back to the definition of freeway. So like it says here, a freeway may be defined as a divided highway facility with full control of access and 2 or more lanes for exclusive use of traffic in each direction. So if you have only 1 lane in each direction, that's not a freeway. The freeway is the only type of highway facility that provides complete uninterrupted flow. And what that means, you have no at-grade intersections, no direct access to or from adjacent property, and ramps are generally designed to permit high-speed merging and diverging maneuvers, and thus minimizing disruption to the mainland traffic. Highway systems are composed of a number of different elements that require different consideration for capacity and level of service analysis. In the case of freeways, these include basic freeway segments, which are segments of the freeway that are not affected by merging or diverging movements at nearby ramps or weaving movements. This would be, for example, an area like this. Notice that this is what we're analyzing, and we're saying it's not affected much by ramps or weaving sections. But in the analysis, later on, we will see that we do consider how many ramps are in the vicinity, and the vicinity means 6 miles of the section of analysis. And that's because these elements, they do have some effect on the freeway performance anyway. We also have ramp junctions, which are points at which on and off ramps join the freeway. That would be something like this, like in this case, an on-ramp junction. These points form an area of turbulence due to concentrations of merging or diverging maneuvers. And finally, we have weaving areas, which are segments of the freeway where 2 or more vehicle flows must cross each other's path along the length of the freeway. And here we have an example of a weaving section where you can see vehicles trying to leave the freeway, or vehicles trying to enter the freeway, or even vehicles trying to go through, have to cross their paths. This is an example of what we mean by a basic freeway segment. Here we have a complex freeway system. We have connections between the different freeways with these ramps and these loops. And then we have here, this would be an off ramp. Here we have an on ramp, and so on. So when we say we're analyzing basic freeway segments, we're analyzing segments like these, no on ramps or off ramps. But typically you will look over a longer segment, analyze how many on ramps and off ramps you have. So that would be a variable because the performance of this segment is affected by things like that. What determines the highway capacity? You can see this a nice picture because it's an excellent example of what we mean by capacity. If these guys are moving, let's say 40 miles per hour, they have to maintain certain spacing, right? So it would be difficult to achieve a higher flow than what you see in this picture. And notice that it's a very peculiar type of traffic. Come, you notice that most of them are passenger cars. You have some pickups that we consider for practical purposes as passenger cars or traffic analysis. What would affect the number of vehicles that you can move per unit time? If you have only 2 lanes versus 5 lanes, there's typically some more freedom to move. There are more opportunities, particularly for the guys that are traveling in the middle, to move to the right or to the left to pass one guy that is moving too low or leaving too much of a gap. So the number of lanes affects somehow the capacity, how many vehicles, the maximum flow on that facility. The lane width also affects how easy it is for people to maneuver. So you tend to lower speed when you feel more constrained, and that also affects the capacity. The shoulder width has a similar effect to what I mentioned for the lane width. You're going to see that the vehicle composition, meaning whether we have tracks or not on the traffic stream, also has an important effect. The median type, the frequency of access to the freeway on ramps and off ramps, driver behavior, whether we have commuters or we have recreational traffic on a facility, and there are other things. So the HCM, the Highway Capacity Manual, quantifies the effect of several of these factors. We will see later how some of these procedures are incorporated. the highway capacity procedures are used for analysis of operations. That means given that traffic and geometric conditions, we need to estimate the level of service of a facility. As you will see soon, level of service is like giving a letter grade to a facility, with A being the best and F mean failing. So you obviously want to assess how your facility is operating. It's also used for design. If you set a policy that a facility should operate at a given level of service, let's say level of service C, then given the traffic and some other geometric conditions, you need to determine the number of lanes that will result in that level of service or better. The way we use it for design is that someone sets a policy for our highways, we're going to have level of service C. So then we have to make sure that our highways have a sufficient number of lanes to achieve that level of service. And we can also do this for planning. Planning is basically kind of like a design, but where the information is a lot less certain. We are assessing whether a facility should be constructed in the first place. Let's start talking about what we mean by capacity. The Highway Capacity Manual defines capacity of a facility as the maximum hourly rate at which persons or vehicles can be reasonably expected to traverse a point or a uniform section of a lane or roadway during a given time period under prevailing roadway, traffic, and control conditions. This is a general definition. It's not just for freeways. That's why it says persons or vehicles, right? So for freeways, we are talking about just vehicles. And notice that it's a very verbose definition, but like I mentioned before, these procedures have been defined by experts that act on committees, and there's a lot of discussion when they define something. So they have to be very careful, and these things have evolved over time. So they're talking about flow. Remember when we define traffic flow, we say we're going to measure things at a point on a highway, and that's why it says to traverse at point or uniform section. So if you have uniform section, that means the flow is not changing of a lane or roadway during a given time period. So when we talk about the capacity, we always were defining a period of time, and typically that would be the peak hour when we have the maximum traffic under prevailing roadway traffic and roadway conditions. What this prevailing here tells you is that capacity we're defining as a kind of an average. You can have actually traffic flows that are slightly higher than your capacity, but those are not sustainable. What this definition is trying to say is that at capacity, traffic fluctuates quite a bit, but during short periods of time, that value can be a little bit higher. Let's define now the level of service. The Highway Capacity Manual employs this concept to represent a qualitative ranking of the traffic operational conditions experienced by users of a facility under specific roadway traffic and control conditions. And it says here it's present because, for example, on freeways, we typically don't have any control. We never stop vehicles with a signal or things like that, right? Notice that this definition does not include safety, and we use different measures for different facilities. For freeways, we will be talking about density. The delays is what we typically use to assess the level of service on traffic signals. So we're going to be looking at how we determine level of service for a facility, and the measures we use to assess the level of service will be different for different facilities. So let's start with freeways. Let's concentrate on those. And let me emphasize what a freeway is. It may be defined as a divided highway with full control of access and 2 or more lanes for exclusive use of traffic in each direction. We mentioned that already. They provide an interrupted flow, so there are no signalized or stop control at graded intersections, and direct access to and from adjacent property is not permitted. Another defining characteristic of freeways is that the access to and from the freeway is limited to ramp locations. Actually, this is kind of like redundant here. But another defining characteristic is that opposing directions of flow are continuously separated by a raised barrier, an at-grade median, or a raised traffic eye. Now, this is important. The operating conditions on a freeway result primarily from interactions among vehicles and drivers in the traffic stream and between vehicles and the drivers and the geometric characteristics on the freeway. That means we don't have any elements on the freeway itself that are going to control that traffic flow. It's just arising from the interaction between individual drivers. Of course, operations can also be affected by environmental conditions. You may have noticed typically when it rains, people take slightly longer distance between cars, so the traffic flow typically get reduced. So weather and lighting conditions make a difference. Pavement conditions can also affect the operations, and by the occurrence of traffic incidents, like we have seen on shock weather. As I mentioned before, of the three types of elements we have for freeways, we're going to concentrate on these, which are the basic freeway segments. What we're looking for capacity analysis is nothing more than a simple application of some of the things we have learned for traffic flow analysis. So basically we have flow speed relationship with the speed in the vertical axis and flow in the horizontal axis. As we discussed before, we have an uncongested regime portion is the top part here. So we would have, this would be an uncongested portion. And obviously the lower part would be the congested portion. We will be talking about the free flow speed, which is when the flow or the density are equal to 0. And we will have a capacity, which is basically the maximum flow. So the same concepts we have seen before are described here. And really what the highway capacity analysis that we're going to look at a lot of different details, but it boils down to the following. If you remember the fundamental traffic flow relationship, Q equal KU, and I just told you density is what is going to be defining our level of service. So basically we're going to need to find out a speed for a given flow, and the ratio would be given as the density. And that density will define the level of service. So soon I want to present some slides where we will see that this region over here is divided into different areas, something like this. So this would be A, B, C, D. Then we have E. As you can see in this equation here, the ratio of, the flow to speed gives me density. So you can see that the slope of these lines are related to the inverse of density. In here I have level of service A, where the density is so low, so that's why the slope of this line is high, that I have level of service A. If I'm at this point, I will have a level of service B. If I am at this point, I have level of service C, and so on. So the highway capacity procedures boil down to finding this curve, that red line, then for a given flow, determining the speed, and then taking the ratio of that flow and that speed, U, and that defines the density, or simply by looking at where this point falls. We're going to do it numerically most of the time, but if you have the chart, you can do it that way as well. You're going to see some flow charts, a lot of equations, but the basic procedure is really, really simple. Of course, it has some details which we're going to be discussing. A basic freeway segment is typically characterized by three main performance measures: density in terms of passenger cars per mile per lane, speed in terms of mean passenger car speed, and volume, which for capacity analysis typically they define it as volume to capacity ratio. So if we have a capacity and volume is variable, instead of talking about volume, we can talk about volume to capacity ratio. That's what that means. Even though we're saying density defines the level of service, you're going to see soon that once you know the density, you also know the speed, and you would also know this volume to capacity ratio. So in reality, you can use any of them because they are all related, like we have seen before. But still, what is used to define the capacity, and that committee that they developed this manual decided that density was the quality we're going to use. Notice also that they're very specific about the units of density. Before we have talked about vehicles per mile, right? Notice that here it says cars per mile, not vehicles. There's a difference between vehicles, can include cars, trucks, recreational vehicles, and so on. But now they're saying, no, we're going to define density in terms of cars per mile and per lane. So we do the analysis on a per lane basis. The density is going to be defined in passenger cars per mile per lane. So we're going to divide by the number of lanes. So each of these measures, density, speed, or volume to capacity ratio, is an indication of how well or how poorly traffic flow is being accommodated by the freeway segment. And although speed is a major indicator of service quality to drivers, freedom to maneuver within the traffic stream and proximity to other vehicles are equally noticeable concerns. And these two, the freedom to maneuver and proximity to all vehicles, are related to the density of the traffic stream. Also, unlike speed, which we saw in the previous diagram, we have two speeds for a given flow. Density increases as flow increases up to capacity, resulting in a measure of effectiveness that is sensitive to a broad range of flows. This basically is why the experts decide to use density instead of speed. Okay, so based on several of the things we have been discussing, both freeways and multi-lane highways use traffic density for level of service determination. So basically it's an application of the fundamental traffic flow relationship we discussed before. For two-lane highways, they use something that is called percent time spent following and the average travel speed. Percent time spent following is basically what percentage of time you're following another vehicle. I think the definition is 5 seconds behind another vehicle. For signalized intersections, I have again the question here, what do we use? And we already mentioned we use delay. Okay, so let's talk about level of service. So these definitions are in the text. Level of service A is basically free flow operation. You can see here it's vehicles are moving fast, kind of following, but if this guy wants to pass, this guy can move very easily to that lane. So there's practically no friction between traffic, right? So level of service A represents free flow conditions. Individual users are virtually unaffected by the presence of all others in the traffic stream. Freedom to select speed and to maneuver within the traffic stream is extremely high, and the general level of comfort and convenience provided to drivers is excellent. And if you read the definition for level of service B, it would be something similar. I'm not going to read the whole thing, but here you have a kind of a summary: reasonable free flow, ability to maneuver is only slightly restricted. You have a little bit more restriction here than what you had before, but still you are free to move. There's a slight decline in the freedom to maneuver within the traffic stream with respect to level of service A. If you have a minor incident over here, it would be easily absorbed still. On level of service C, you still have speeds that are at or near free flow speed. We have talked about what free flow speed is before, but now your freedom to maneuver starts to be restricted, and if you have some blockage, then you may start having queues forming behind those blockages. Then for level of service D, again, your freedom to maneuver gets more restricted. Now it's kind of severely restricted. Densities increase more quickly, the freedom to maneuver is more noticeable, and now minor incidents can start creating significant queuing, like we saw with shockwave analysis. Then when you go to level of service E, let me read that one. Level of service E represents operating conditions at or near the roadway capacity. So in here, we're very close to what the capacity of the road is going to be. Anything that happens there, it will create significant shock waves and significant congestion propagating upstream. So even minor disruptions to the traffic stream, such as vehicles entering from a ramp or vehicles changing lanes, can cause delays as other vehicles give way to allow such maneuvers. In general, maneuverability is extremely limited and drivers experience considerable physical and psychological discomfort. And then you have level of service F, where there's a breakdown in traffic flow. Level of service F represents really when you have a higher demand than it can pass through the section. And if you want a good example of how that can occur, during significant portions of the day on H1, when you have the H1 and H2 merge, let's say coming to town, immediately after the tunnel, right? 3 lanes coming on H201. You have 3 lanes coming on H201, and you have 2 lanes from H1 joining. So those are 5 lanes, and then those become, I think now it's 4 lanes immediately downstream. You have upstream, you have the demand is higher, so you can accommodate more vehicles upstream, but then when you put them in a bottleneck, which is reducing the number of lanes, those vehicles cannot pass, and then the queue starts propagating throughout the day. So you have the number of vehicles wanted to pass that point of the highway is much higher than, or is higher than what you can accommodate. So during periods of time, you have higher demand than you can accommodate, and that creates level of service F. Whenever you have these shock waves, you have those accordion-like movements that you have stop and go conditions. So that's what represents level of service F. It's force flow. The flow goes at whatever it can go based on what happens downstream. Now we're going to go into more of the details. We just define visually what each level of service means. We have said, well, we're going to use density to define what the level of service is. And this is basically an important table that you have to be aware of. What defines the level of service? For level of service A, we have to have a density that is less than 11 passenger cars per mile per lane. If we want to have level of service B, it has to be greater than 11 or less or equal than 18. It has to be in that range. And I try to be very careful here in making sure that it's clear that if it's 11, it's level of service A. If it's 11.01, it's level of service B. Same thing here, if it's 18, it's level of service B. If it's 18.01, it's level of service C. So if up to 26, it would be level of service C, and so on, right? So the defining characteristic for level of service F, a density that is greater than 45 passenger cars per mile per lane. And like I mentioned before, that represents congested flow conditions where demand exceeds capacity. Okay. And this summarizes what I plotted before theoretically. This is actually a screenshot taken from the highway capacity manual. This is the analysis that we're going to be doing. Essentially, we're going to be defining a free flow speed that will define which curve or whether we are interpolating between one of these curves we're going to use. Then we will need to figure out a flow rate that will take some analysis as well. And with those two, basically, once we know what the flow rate, let's say this is my flow rate, and let's say my free flow speed is such that this is the line I will be using. All we have to do for our analysis is just basically determine where that flow rate intersects the curve. That defines this point here. That point also defines, if I move horizontally, defines at what speed and traffic is going to be. So if I take the ratio of flow divided by speed, that will give me basically the inverse of the slope of this line. And the inverse of the slope of that line is density. This point already I can see it falls within level of service C, or if I take the ratio of B or the flow rate to the speed, what I get, Q over U, it will give me K. It will give me the density. So, and I look at that density in my table, and either way I find that the level of service should be C. So for the example I just was pointing out, I should be getting a density between 18 and 26. So in this case, it seems to be closer to a 26. And you can see the densities are given here. What densities limits each level of service are also given in this graphic. So the procedure really boils down to knowing what to do in this chart, and that's it. It's not that much more than that. I haven't talked about this yet. This has a definition, I have to define that, and I have to tell you how to obtain that free flow speed. But other than that, the procedure is what I just indicated. I just said two things. We need to define this, and we need to find out one of these curves. And you may have noticed, these curves really consist of, all of them consist of a portion here, let's take the 75 miles per hour, a portion where it's pretty much constant, then there will be a break point, and from that point on, it looks parabolic. It's actually a parabolic curve. So we define this curve simply by first thing defining the free flow speed, at what point this is intersected. So this constant here is basically the free flow speed. So that's the first thing we need to define. So these curves are defined by, in the following slide, you see the speed of traffic. So let me repeat here. For this density, if I take this curve here, the top curve, that would be the speed. That would be 70 miles per hour, even though the free flow speed is 75 miles per hour. So there are two different things here. One is the speed at which, for a given flow, traffic is going to travel. And a different thing is the free flow speed, which basically defines the curve. So the equations in the next slide are giving us the speed for any flow rate. So we're going to get the curve. So essentially, what is for a given flow rate, what would be the speed at which traffic is moving. So, and you see this in this slide here. It says the speed, we have two different expressions. The first one, it says the speed is equal to the free flow speed. Remember, I pointed to a horizontal portion of the curve over here. The speed is equal to the free flow speed. For flow rates that are below the break point, that means below the point at which this starts curving, it will be somewhere over here for this curve. For this curve, it will be somewhere over here, for this one over here. So you can see it changes in each case. So the speed is constant, equal to the free flow speed for flow rates less than the flow rate breakpoint, and is equal to this expression, which at first looks kind of intimidating, but it's very simple. That gives me the quadratic function. Notice that it says speed as a function of the flow rate, and I have a square there. Okay? All the other things are constants here. So basically the speed is a quadratic function of the flow rate, And notice that as the flow rate increases, this whole term is going to increase, and therefore, since this is subtracting, the speed is going to decrease. That's how we get this shape coming down over here. Notice also something else here. Let's define the other terms. So the first term is the free flow speed. Notice that when this term becomes 0, and that happens at the break point, the speed is equal to the free flow speed. And obviously that has to be the case because these two things at the break point become equal. And why do I say that at the break point becomes 0? Because if the flow rate is equal to, in value to the break point, this difference is 0. So in that case, this whole term becomes 0. Now, if the flow rate is equal to the capacity of the road, so in this expression, C is the capacity in passenger cars per hour per lane. Again, we're working on a per lane basis for flow rates. So we have capacity minus, if the VP is equal to capacity, we have capacity minus breakpoint squared divided by capacity minus breakpoint squared. So this ratio here, the ratio of these two quantities, is equal to 1. Okay, and so I will end up with free flow speed minus free flow speed, that would be 0, minus with minus, it would be plus the capacity divided by 45. And remember, 45 is the density defining the capacity of a road. So we will have capacity, which is a flow, divided by density, that gives us a speed. That gives us the speed at which traffic is flowing when we have capacity conditions. So it gives us this speed over here. Okay? In between those 2 points, between a flow equal to the break point and a flow equal to the capacity, between those two, this value will always be less than this. So this ratio will always be a value that is less than 1, but it's going to be variable. And that's why this will be moving between the free flow speed and the speed at capacity. Okay? So that's how they formulated this equation, so that this always happens. And then you may be wondering, okay, how do I get that capacity? Well, that capacity is defined, and again, it's a function of the free flow speed, which we have not talked yet how we get that. But if I knew the free flow speed, I get this expression for the capacity of the road. It says here is the minimum of either 2400 or the result of this expression, which is 2200 plus 10 times the free flow speed minus 50. So this expression is valid for values of free flow speed between 55 and 75 miles per hour. So what this says is that sometimes I can get a value that is higher than 2400. If that's the case, I will use 2400. In any other situation, if I get here 2300, I will use the value of C equal to 20. So let me just do one calculation. Let's pick one value. Let's pick 60. So if I have 60 minus 50, I'm making that calculation there. That gives me 10 times 10 gives me 100. And if I add that to 2200, I get 2300 for this expression over here. So for 60 miles per hour, I got 2300, and compared to 2300, the minimum is 23. So my C would be equal to 23. Let me just repeat that. So if I have a free flow speed, if my free flow speed is 60, this becomes 10, and this multiplication becomes 100, and this whole number becomes 2300. And obviously, in that case, my capacity will be equal to 2300, which is the minimum of 23 and 24. Okay? If I plug in the value of 75, let's do the same thing, but for 75. With 75, 25 times 100, we get 250. And then the whole result here becomes 2450. And in this case, the capacity of the road would be the minimum of the two, which is 24. Okay, with that, let's continue next class. And sorry I took 3 additional minutes. Any questions before we move on?
So if that number is greater than 2400, we use 2400?
Exactly, that's what it is.
Okay.
Okay, perfect. Okay, I'll see you next class then, guys. See you.
I have one.
Yeah, okay.
So the 45 in that equation, since it's the density at capacity, will that change, or was it always a flat?
No, it's always fixed. It's always fixed. You see, here we have the line for the capacity. Notice that that's 45. It's fixed. It's valid for all these curves here. It's always 45, right? So it never changes. The speed at capacity changes, and the flow at capacity changes, but not the density. So that's why they fix that value at 45.
Okay.
Okay.
Thank you.
Thank you, guys.
Thank you.
But the other day we finished talking about this chart, which basically summarizes what we need to do. Remember, I had quite a bit of a discussion. Basically, we said capacity analysis boils down to determining a flow rate, which I still have to define what do I mean by flow rate, what's the difference with traffic flow that we discussed before. For a given flow rate that we need to determine, then we're going to get a point here on a given curve that we also have to determine. We have to determine which of these curves we're going to use. Right now, I'm saying I'm going to use this one. And once you do that, for that curve, you get a given speed. And once you have a speed and flow, flow divided by speed is density, right? The inverse in this graph, because we have flow in the horizontal axis. So if I join this point with the origin, the inverse of the slope of that line is what the density is. So basically, once we find the point, we are defining the density, and remember that density was what we used the other day to determine level of service. And that's all there is to this capacity analysis procedure. Let's look at the details and some examples. The other day I started saying, okay, how do we find these curves? So we need to define a speed, what we have in the vertical axis, as a function of the flow rate. Once we figure out, and we still don't know how we figured out this, which of these curves we're going to use, but let's say we use the one for 70 miles per hour, I need to have an expression that defines that curve. And that's where I spent quite a bit of time the other day, and we finished with this, saying, oh, it's the speed is equal to the free flow speed up to a certain breakpoint, and beyond that point is a quadratic expression. Again, I defined the details of that expression the other day, so let me move on from there. That expression was a function also of the capacity of the road, and we said, well, that capacity is given by this expression, which was the minimum of a function of the free flow speed, what we have here on the left side, or 2400. Whichever is the minimum, that's the value we picked. So, and that's valued between 55 and 75 miles per hour. That's what the high capacity manual used. And I think that's where we stop, right? Now, in this expression, there was a breakpoint, and the breakpoint, let me just emphasize what that is. Notice that for 75 miles per hour, the connection between the constant and parabolic portions is around there, right? For the 70 miles per hour, it seems that around there is where the drop starts. I'm not sure, it's something around there, right? So just eyeballing it. So for 65, it seems that around there, for 60 is around there, and for 55 is around there. So it's probably not perfect what I'm doing, but you can see that the breakpoint is a function of the curve that I'm picking, and that curve, it depends on the free flow speed that defines the curve. So those points where the curvature starts, it's also variable, and it's given by this expression. So that's what defines those curves. This another table is table 6.2 in your textbook, that basically for each level of service tells you what's the maximum density that you can have and still be in that level of service. So for level of service A, the maximum density would be 11. So from 0 to 11, it's level of service A. From 18 to 18 would be level of service B. From 18 to 26, level of service C, and so on. And that's basically the same criteria on another table that I showed you the other day, that is also in your textbook. It's basically the same information put in a different format. But this table, notice that we have the 4 different pieces of information for different free flow speeds. Free flow speed of 75, free flow speed of 70, and the table continues with 65, 60, and 55. I just put the information for 2 of the speeds in these notes. Notice that it doesn't matter what the free flow speed is, the density defining the level of service is always the same, right? So for level of service C, it's always 26, for level of service D, it's always 35, and so on. Now, the table also gives you other information that you can see here: average speed, maximum volume to capacity ratio, and maximum flow rate. And what you should understand is that once we define this density, everything else for one free flow speed, for a given free flow speed, everything else could be defined. So whether I talk about this or that would be equivalent. So let me point out what these things are. Notice that for average speed, we have the values for 75 miles per hour free flow speed. We have 75, 73.9, 68.3, 60.9, and 53.3. Let me point out what those are. Basically, we're saying that for this limiting value of 11, the speed coming from this curve for that flow rate is 75. That was the first value we had. For level of service B, which corresponds to this flow rate, we had something that was slightly lower. It was 73.9, I think it was, right? So you can see it goes down a little bit. For level of service C is this value, what you find in that table. It corresponds to this flow rate, and a speed that is slightly less than 70 miles per hour, and so on. You get the speed for this value and the speed for that value, and so on. So those are the values that you see here. You see 73.9, 68.3, 60.9, and 53. So that's defined by the curve, corresponds to 75 miles per hour. If I pick the one for 70 miles per hour, the values that I see here are the ones that I obtained by doing the same thing. Is this intersection here, 75 miles per hour, or this intersection, which is pretty much 70 miles per hour, or this one, which is somewhere between 65 and 70, or that one, which is almost 60, and then that value, which seems to be about 55. So these are the values, yeah, 55, that's the problem with reading charts, it's 53.3, the exact value. Notice that the maximum flow rate is the maximum flow rate corresponding to that level of service. So it's basically the other thing I had been pointing out. Remember I told you for each of those points that I've been indicating, I've been telling you, let's pick 65 miles per hour. For 65 miles per hour, I've been pointing, that's the limiting value for capacity. So I mentioned we get a speed, reading here, and we get a flow rate, which is the value that I'm pointing out here. For level of service B, the flow rate would be this value. For level of service D, it would be this one. For level of service E, it would be this one. And obviously for level of service F, it would be that one. So for each level of service, I can get what's the maximum flow rate that defines that level of service. So any flow rate below that, it will be level of service A. Any flow rate below this corresponds to level of service A. Any flow rate between these two values corresponds to level of service B. Any value between these two corresponds to level of service C, and so on. These values, this one, which is about 700 roughly, I'm looking from the chart. This will be about 1200 and so on. These values for 65 miles per hour free flow speed, sorry, I don't have 65 in here, but those are the values that you see in this row. Okay, if I had picked the curve for 70 miles per hour, these are the values I would be reading there. So let me just go back. You can see the flow rate for 70 miles per hour is a little bit higher for level of service A, and for level of service B, it's also a little bit higher, and so on. Okay, so knowing that, if that's clear, then we have another growth here that says maximum volume to capacity ratio. This is basically the maximum flow rate divided by the capacity. And let's just point out, if we pick these values that we have here, the capacity for this one, for this curve, is this value. So obviously for level of service, the limiting value for level of service E is a volume to capacity of 1, because that was the limiting volume for that level of service, and that also happens to be the capacity of the road. So the ratio between the volume and capacity is equal to 1. For this one, it would be a value, for all the others, would be a value less than 1, right? So in here, it would be a value closer to 0 than in here, that would be a value closer to 1. And that's basically what you see in that row. And notice that the capacity, not just the flow rates, but the capacity is also changing with the free flow speed curve that you select. So that's also given in this table. These are the values that you see here. So where we talk about maximum volume to capacity ratios, or maximum flow rate, or average speed, they're all defined. So let's talk about the determination procedure for level of service. It has 4 steps. First, we're going to need to establish base conditions and capacity. Then we're going to estimate or measure the free flow speed. We're going to calculate an analysis flow rate, and you're going to see these are the 2 main things that we need to do in this procedure. And with that information, we're going to calculate a service measure and determine the level of service. Okay, so this is a very rough idea of what we have to do. I like this a lot better, which I took from the highway capacity manual. I don't think this is in your textbook. This is basically the procedure that we're going to be following. It has basically the 4 steps that I mentioned before. This would be step 1, this would be step 2, this would be step 3, and this would be step 4, but with a lot more details. We're going to need some geometric data, and either a field measure free flow speed, or we're going to assume a base free flow speed that we're going to later modify. And we will need to have volume information. Volume is how many vehicles per hour are we estimating in the peak hour in our transport. Once we get our information, we're going to go and either we have to complete these 2 different branches. So I have to go here, and this side is to compute the speed. And as usual, if you have an existing freeway, the best thing to do is go and measure things in the field. And measuring things in the field may be just getting information from a traffic sensor. So that may be there, or worst case scenario, particularly for lower volume roads, and I mean, not freeways, but for tuning roads, other type of facilities, many times you would go and actually measure free flow speed. But for freeways, most of the time, we may have some sensor data. So the best thing is, obviously, if you have the information, measure it. But obviously, for new freeways, you cannot go and measure anything because the freeway doesn't exist. So in those cases, or when it's not possible, we don't have sensor information, we are going to assume a base free flow speed, and then we're going to adjust it for different things. The width of the lanes, how many lanes we have on the facility, how many interchanges are close by to the section we're analyzing, and the right lateral clearance, how much clearance we have on the right shoulder. And with that, we're going to compute a free flow speed. So this would be one of the things we need. Basically, remember when we look at the previous graph, I told you we need to define which of those curves we're going to be using. Once we know the free flow speed, that's telling us which curve we're going to use, or if we have to interpolate between some of those curves we have in the previous graph. So we need to come up with whether I'm going to be using 70 miles per hour or 75 or 65 or somewhere in between. The left of that chart that I was just talking about was defining this, which curve I'm going to use. The other side of the chart is basically saying, okay, for what flow rate I want to determine my level of service. And once I do that, this point falls in this region, which corresponds to level of service C, and that's it. That's all there is to it. So the last part of the chart is basically doing what I'm doing here, which is moving in this line and determining where we are. Computing the flow rate, that's what we see on this side of the chart. And for that, we're going to have a certain volume. It's what before we have called the traffic flow. Now we're going to call it volume in terms of number of vehicles per hour. We will adjust by the peak hour factor. We will define that soon. Also, it's going to be affected by the number of lanes. I forgot to take, I thought I had taken this one. This one doesn't appear in your book anymore. It was updated, driver population, but it is still there in special procedures, but not anymore in the base. And we're going to adjust that for heavy vehicle. You can see that with this, we are trying to take into account that traffic is not uniform during the peak hour. With this, we try to account for the fact that the number of lanes also affect the flow rate. And with this, we try to account for the fact that not all vehicles are equal. Trucks are not the same as cars, so they consume more space. So once we do those two things, this one defines the speed flow curve. And with this flow rate, for a given speed flow curve, we can determine what speed we have. And remember, the ratio of flow to speed gives us the density. So with that, we will be able to compute the density, and that basically determines the level of service. These four things basically finding that point that I told you previously that defines the capacity. So let's talk about freeway-based conditions. When the free flow speed cannot be measured, the Highway Capacity Manual 2000, and actually I forgot to update this, should be now 2010 or 2016, the procedures produce an initial estimate of free flow speed of a freeway under the following base condition, and then modifies it to capture the effect of any deviation from the base conditions that are present at the freeway section under study. This is only when you are making the estimate. So let me just define the base conditions. Base conditions are, we have 12 feet minimum lane width. So anything beyond 12 feet lanes, it would meet the conditions for base conditions. You also require a 6 feet minimum right shoulder clearance between the edge of the travel lane and objects like utility poles, retaining walls, traffic barriers, etc. that influence driver behavior. Anything that is really close to the freeway, it makes people try to shy away from those objects. We're assuming that we have only passenger cars in the traffic stream. That's usually not the case, right? So, but for the base conditions, we're assuming we have all passenger cars, and that includes pickups too. And then we have an interchange drum density of 6 miles or greater. And we also have level terrain. That means no grades that are greater than 2%. Nothing that can actually affect the traffic speed. Okay, so let's start defining some of these things. Lateral clearance, you can see basically on this freeway, and remember what defines a freeway is whether you have access control, you don't have access from these abutting properties. So this is an urban freeway, obviously. You have here very little clearance on the right side, very little clearance on the right side. So that affects traffic quite a bit. On the other hand, here, this is much more open in the direction, on the right side of this direction of traffic or the right side of this direction of traffic. Clearly, this is a lot more generous and it affects a lot less traffic flow on this freeway than what we have here. So lateral clearance is important. How we determine the basic free flow speed, we have two options. One is go and measure the free flow speed, or you can use this procedure to come out with a free flow speed. So let's look at that. Again, so this is what I just said, that we can go and measure it. If you actually measure the speed, so if you get it from sensors, you get it from sensors. You don't have to worry, just have to make sure that you are talking about passenger cars. And the other thing you have to do, if you actually measure it with a radar, you have to make sure that you don't bias the data. You don't want to be with a radar and being very obvious, because people, when you see someone with a radar, you think it's a police, and then you reduce the speed. So you end up affecting what you're trying to measure. Okay, or if you are very close to the road, you may cause lateral displacement that also affect traffic flow and so on. This is about how you measure speed. I'm going to skip that. If you have to estimate the free flow speed using the high capacity procedure, the first thing you're going to do is assume a base free flow speed. And the base free flow speed is always 75.4 miles per hour. So that's what we call the base free flow speed. So you start with that value, you put 75.4 in there. And then we're going to adjust that value by the things that we have been talking about. The adjustment for the lane width, another adjustment for the right shoulder lateral clearance, and I think now they call it FRLC because right lateral clearance. And then we're going to adjust for the total ramp density. So we're going to look at the factors for these two, and then this is just part of the equation. We're going to see how we compute that total ramp density. So let's look at that very quickly. The adjustment factors, these two, you just simply find them in a table. And notice that the adjustment factor has the same units as the speed. So these are base free flow speed, and this is the free flow speed. It's something we're going to subtract. So notice that if we have 12 feet lanes, remember that 12 feet is the minimum for the base conditions. If we have base conditions, we make no adjustment. The adjustment for lane width is 0. Now, if we have 11 feet lane, the adjustment is 1.9. So we will reduce the base free flow speed by 1.9 miles per hour. And if we have 10 feet lanes, we will reduce them by 6.6. For freeways, typically, we shouldn't be less than 10 feet. And obviously, you can interpolate in between. I'm going to try to avoid interpolation in this class. Then the adjustment for right shoulder lateral clearance is just looking again at the table, and the adjustment factors, you find them in this area of the table. And it depends on two things. It depends on the total number of lanes. And by the way, be careful, read the tables carefully, right? If I have a 4-lane freeway, typically that would be 2 lanes in each direction. So I would have to look at this value. If I have a 6-lane freeway, typically we'll be looking at 3 lanes in each direction. So we'll have to look at this. This corresponds to an 8-lane freeway, and this corresponds to a 10-lane freeway. So typically when we talk about how many lanes we have in a freeway, it's total in both directions, but then the analysis is directional. So don't get confused with that. So number of lanes is important, and the other thing that is important, obviously, is the lateral clearance. 6 feet was the condition correspond to base conditions, so 6 feet or more. If I have 6 feet or more, my adjustment is basically nothing. I will not adjust the base free flow speed for lateral clearance. But if I have 5, I will start reduced by the lateral clearance. And then if I have 0, the reduction will be a lot higher. It's 3.6 miles here, 2.4 here, 1.2, and 1.6. You can see that as the lateral clearance gets smaller, the adjustment factor gets higher for a given number of lanes in the direction of analysis. But also for a given lateral clearance, the adjustment factor depends on the number of lanes. You can imagine why that is. If I have a freeway and I have many lanes, and I have a vehicle here, if I have an obstacle here very close to the freeway, this vehicle will be affected. It will tend to shy away, will move to the side of the lane. And that may affect that vehicle coming on this other lane, which also may shy away a little bit, but then the vehicle in the next lane is going to be affected less. So overall, over several lanes, is less of a problem than if I have only 2 lanes, right? Because if one vehicle here shies away because of that, then the next vehicle doesn't have much space to shy away to the left. Like you have a lot of room to accommodate sudden movements. That's why it becomes less efficient when we have fewer lanes than when we have more lanes. So all you have to do is just pick one of these values corresponding to the number of lanes in one direction and lateral clearance. That's it for lateral clearance. And then we have the total ramp density. Total ramp density refers to the number of on and off ramps 3 miles upstream and 3 miles downstream of a segment midpoint, divided by 6 miles. So essentially, you take a segment of 6 miles centered on your portion of the freeway of interest, count the number of ramps you have, on ramps and off ramps you have on that segment, and divide by the length of those 6 miles that you selected. And with that, you get the total ramp density. So we will see how we use that information in detail in the example. Now let's go to the volume adjustment. So let's define what these things are. So this is what that side of a chart that we need to apply adjustment for peak hour factor, adjust for vehicle mix, adjust for vehicle population. This will define these three factors that we see in this equation. The value defined here as hourly volume will have to be divided by these three factors, and that will define the traffic flow rate. So let me start talking about these things. Let's define the hourly volume. Notice that it says for all lanes in analysis direction in vehicles per hour. Clearly, most of the time what you will get is some estimate of the annual average daily traffic for your freeway. With that, you will have to come up with an estimate of an hourly volume, which is typically given in vehicles per hour. And that would be for all lanes in the analysis direction. So this is determined in vehicles per hour. And vehicles encompass anything: cars, trucks, motorcycles, everything. And it's total for all lanes. Clearly, if I want to be doing the analysis on a per lane basis, it's clear you need to divide that number by the number of lanes. Because once I divide the total traffic B in vehicles per hour by N, now the units of this is going to be what I had, vehicles per hour, but now also per lane, right? And then we have two other factors. This one, the peak hour factor, is used to account for the fluctuations in traffic. So even though I'm talking about the peak hour, and by peak hour meaning the hour with most traffic throughout the day, I still have fluctuations within that hour. So I'm going to divide that by a number that is less than 1 to make it higher, to account for the fact that during 15 minutes of that hour, traffic came out to be higher than the average of the hour. We have just seen queuing analysis, and you saw how demand during a period where you cannot cope with creates queuing, and that queuing creates a lot of delay. We have seen that, and that's why the heavy capacity model tries to account for the worst conditions. That's why they divide by this factor. Okay, and then we have this other factor, the heavy vehicle adjustment factor, that essentially it's also a factor less than 1 that makes the volume now even higher. But now when we divide by this factor, we're going to go from these units, vehicles per hour per lane, to passenger cars per hour per lane. So we're going to increase this volume. This ratio is going to make that quantity be even higher, because now you account for the fact that if you convert trucks into an equivalent number of passenger cars, that gives you more or less the same service conditions. You have to realize that when I have trucks in general, the service is worse, right? So in order to make a traffic volume or a traffic stream that includes trucks equivalent to just a traffic stream of cars, that traffic stream of cars has to be higher. Volume is the number of vehicles passing a point on a highway or highway lane for 1 hour, expressed as vehicles per hour. That's the same thing we have defined before as flow, right? These are the definitions of the heavy capacity manual. So for the heavy capacity manual, they are very specific, and they define a flow or flow rate as the number of vehicles passing a point on a highway or highway lane during some period of time less than 1 hour, expressed as an equivalent rate in vehicles per hour. The key is here, we are taking a time that is less than 1 hour. For freeway analysis, typically the value would be 50 minutes. In some other analysis, they make analysis with 5 minutes. So I have some examples here with 5 minutes, but just be clear, for freeway, typically we talk about 50-minute period. So let's say you count 100 vehicles in 5 minutes. So let's take a 5-minute period. If I were going to express that as an equivalent flow rate in vehicles per hour, so I have 100 vehicles per 5-minute period, but how many 5-minute periods I have in 1 hour? 12, right? So you multiply 5 times 12, you get 60 minutes. So I have 12-minute periods in an hour. Those 100 vehicles per 5-minute period are flowing at an equivalent rate of 1,200 vehicles per hour. Is that clear what a flow rate is? It's basically the same as the volume, but you determine it over a shorter period of time. And then you expanded it as if that has happened in the whole. The peak hour factor accounts for what happens in the most congested 15-minute period within the peak hour. Let's remember that the consecutive 60 minutes of the day when a highway experiences the highest volume, or equivalently, the highest count of vehicles in an hour, is known as the peak hour. The ratio of the peak hour volume V to the maximum rate of flow Q based on an interval T less than an hour is known as the peak hour factor. For the analysis of freeway capacity and level of service, the interval T selected is 15 minutes. This is the equation for the peak hour factor, where we have V divided by this quantity, which is the flow rate QT, which can be expressed as the product of two factors, VT and 60 divided by T. Let's clarify what these quantities are with an example. Here we have 4 15-minute counts. These are the counts. within an hour, which happens to be the peak hour. In this example, the volume is simply the sum over the peak hour of the 4 15-minute counts. In other words, we have to add up 300 plus 400 plus 320 plus 280, which adds up to 1,300 vehicles, and therefore our volume V is 1,300 vehicles per hour. The number Vt in this denominator corresponds to the maximum number of vehicles counted during one of the 4 15-minute intervals. So in this example, again, that number happens to be 400, which is multiplied by the number of 15-minute intervals in the hour, which is clearly 4, to yield the flow rate Qt, or in this example, Q15, which is the maximum flow rate based on a 15-minute count, but expressed in vehicles per hour. For the example at hand, we have V, we mentioned it was the sum of these four values, is 1,300 vehicles per hour. The maximum count was 400, and then that's multiplied by 4. So we end up with 1,600 in the denominator, 1,300 in the numerator, and the ratio is approximately 0.812. Let's look at two examples, and I typically pick examples that are extremes. So let's look at uniform demand. Uniform means that demand doesn't change. So let's read this. Assume that 50 vehicles were counted during each of all possible 5-minute intervals during the peak hour. Compute the peak hour factor. So in this case, the total number of vehicles that were counted are 600, because 12 times 50 is 600. And since we have perfectly uniform demand, that means the number of vehicles arriving constantly at the same rate during the whole hour. If we were going to take the maximum, it's any of those 50. So 50 times 60 divided by 5, which is multiplied by 12, is also, the flow rate is also 600. So the volume is 600 and the flow rate is 600. So in this case, the peak hour factor when you have uniform traffic demand is exactly 1. Let me go to the other example, which is more illustrative. Extremely peak demand. Let's say we have a case where we have 200 vehicles were counted in a 15-minute period. Notice I changed the counting period now in this example. And no vehicles were observed during the rest of the hour. So the volume now is, in the hour you counted 250 vehicles. That's it. The 250 vehicles you counted in this 15-minute period is the total number of vehicles you counted in the hour, because the rest of the hour you had no vehicle. In terms of the rate of flow, you counted 250 vehicles in a 50-minute interval, and now you have 60 divided by 15 for 50-minute intervals per hour. So if you multiply 4 times 250, obviously this count is equivalent to 1,000 vehicles per hour. So in that case, your volume is 250, your flow rate based on the 15 minutes more congested period is 1,000, so the ratio of the two is 0.25. So in that case, the peak hour factor is 0.25. Notice that it happens to be equal to 1 divided by the number of time periods you have in the hour. That's an extreme. How many times you're going to count 250 vehicles in 15 minutes and 0 in the rest of the hour? That doesn't happen, right? So it's this completely artificial, but the point is that this is the minimum you can get for 15-minute periods, and the maximum you can get is what we did in the previous example, which is 1. So the peak hour factor is always less or equal than 1 and greater or equal than 1 divided by the number of periods, T in the hour. So in this case, I use 4 because in this example, I use 15 minutes periods. In the previous example, I have used 5-minute periods. In that case, that would be 1 divided by 12. So if you were going to use half an hour, it would be 0.5. The reality is that the peak hour factor typically range from 0.7, 0.75, 0.8, 0.9, close to 1 when demand becomes more unique. Let me try to make it clearer. Say we take counts over 50-minute periods. So in the first 50 minutes, I counted 100 vehicles. In the second 50 minutes, I counted 50. In the third period, I counted 250. In the fourth, 100. So if I add these counts, I counted 500 vehicles over a period of an hour. So my volume is 500 vehicles per hour. To define the peak hour factor, I take the maximum count. So in this case, the maximum is 250. And I multiply by the number of 50-minute periods I had in the hour, which is 4, and I get 1,000. So in this example, the peak hour factor is equal to 0.5. And just to repeat, typically you will enter the procedures with a volume, and that volume, B, is given as a total for all lanes. That's why you divide by N to make it on a per lane basis. And now you divide by the peak hour factor to increase it to account for the non-uniformity of demand.
For the extremely peaked demand volume, Why did you not multiply that by a number? Like in the uniform demand, you multiplied 50 vehicles by 12 to get the volume. So why were the 250 vehicles, why
Well,
isn't that being
let me try to
multiplied?
clarify that with this example. The first example was I have 250 here and I have 250 here. So all this would be red, right? And this would be red and this would be red. That would be perfectly uniform demand. On each period, I measured exactly the same. So my volume is 4 times 250. And if I pick any of these and I multiply by the number of 50-minute periods I have in this example, I get the same thing, 1,000 in both cases.
Oh, okay, got it. Thank you.
The second example was basically saying I have no traffic here, that's 0, so I don't have that bar. This is 0, this is 0. So my volume was 250. I counted vehicles over this whole hour and I counted only 250. But if I take the most critical 50-minute period, which is this one, and I multiply by 4, during that 50-minute period, the traffic was flowing as if in the hour I have had 1,000 vehicles per hour. It's not real, right? It's accounting for that short period of time where the demand was higher than usual. So that's is flowing at an equivalent hourly rate of 1,000 vehicles per hour. The volume is lower, it's 250 only.
Okay.
So we are making analysis. In reality, what we're going to be doing is making analysis with vehicles per hour, but we're analyzing the most critical 50-minute period. That's what basically we're doing with this analysis. And that's why we increase that volume to account for that. Like I said, these two examples are extremely unrealistic conditions. Most of the time, you're not going to get that much variation. And here I put between 0.8 and 0.95. Those are typical values. The closer the peak hour is to unity, the more uniform the demand is. And the closer the peak hour factor is to 0, the more peak the demand. Okay, so, and this is the equation you have in your book, which actually is simpler than what I've been showing before, but it's basically the same thing. This is the flow rate in the 50-minute peak period, and this is you multiply by the number of 15-minute periods you have in your book. And your book uses 4 because for freeways we typically use 15 minutes. So this is the VT that I had before. The T was playing the role of how many minutes you're using for count. So we will be using that equation a lot.
We'll only be using that if we're looking at the 15-minute interval.
Yeah, for the most part, we're going to be using this equation. Excuse me. Let's talk about now the other adjustment factor we have. When you take the Pali or H3, any road with a steep slope, what happens when you get behind a truck? They have a harder time negotiating rates, right? So many times they can go very slow, and that obviously affects everybody on the freeway. The other thing that happens is, notice the gaps between vehicles in here. It's difficult to quantify, but they tend to be short. When you follow a truck, do you guys follow them at the same distance that you follow another car? We typically don't, right? Because you cannot see anything ahead of you, in front of you. You see just the truck. And if the truck suddenly stops you, people in general, they tend to leave a larger gap behind a truck. At the same time, the truck's braking capabilities are not as great as cars. So because of that, they also tend to leave a bigger gap. So in general, trucks occupy more space. We tend to leave more space, and truck drivers tend to leave more space. So because of that, and the acceleration capabilities of trucks and cars are not equivalent in terms of the capacity they consume of the road. We are going to be using some equivalence between cars and trucks. We need to account for the traffic mix, and basically what we do is a two-step procedure. In the first part, basically we're going to determine a passenger car equivalent, saying, okay, each time I see a truck, it will be equivalent to so many cars. So these are typically defined with passenger car equivalents, or sometimes they use the symbol ET for equivalent for trucks. And they have simplified this a lot. Now it's basically we get one passenger car equivalence, and that may depend, particularly for some type of procedures, on how many single unit tracks and tractor-trailer tracks we have. We'll see that later on specific rates. But basically, once we figure out that passenger car equivalent, the second step would be to use this equation that you see here, which is a function of the proportion of tracks in the traffic streams and that passenger car equivalent that you determine. With that, we determine the heavy vehicle adjustment factor. So let me try to define that equation. First, let's define what passenger car equivalents are. They represent the number of passenger cars that would consume the same amount of roadway capacity as a single heavy vehicle. So basically, if you have a passenger car equivalent of 3, it means that a truck is equivalent to 3 passenger cars. So these are functions of the roadway grades or the type of terrain you have. We have a problem. not a problem. It's the highway capacity manual does two types of analysis. One for what they call extended freeway segments. These are extended lengths of freeway containing a number of upgrades, downgrades, and level segments as a single uniform segment. Okay? So the important thing is that grades do not impact significantly on the overall operation of the general segment. And you will see we'll have two types of terrains, two types of extended freeway segments, level and rolling terrain. Or when you have a significant impact of grades, when you have relatively long steep grades that have a significant effect on traffic flow, you will do a specific grade analysis. So for the general freeway segments, if you have grades that do not significantly affect the performance of the freeway, you have an upgrade followed by a downgrade. They're all relatively small. For general freeway segments, you have segments that are short enough and small enough that they don't affect the speed. So as a guideline, this procedure of external general freeway segments can be used where no one grade of 3% or greater is longer than 1/4 of a mile. That's pretty short, right? You may have a grade that is relatively high, but it doesn't have to be more than 1/4 of a mile. And where no one grade of less than 3% is longer than half a mile. So even if you have smaller grades, they have to be relatively short. The road may be going up and down, but very mildly. That's what that says. Otherwise, you have to use a specific grade analysis. So whenever extended general segment analysis is used, the terrain must be classified as either level or rolling. Level terrain is given by this definition, any combination of horizontal and vertical alignment that permits heavy vehicles to maintain approximately the same speed as passenger cars. And that generally includes short grades of no more than 2%. For the class, I will tell you we either have a level terrain or a rolling terrain, where we have the combination, the definition here, or an extended freeway segment. I'm just going to read what the rolling terrain is any combination of grades and horizontal or vertical alignment that causes heavy vehicles to reduce their speed substantially below those of passenger cars, but that does not cause heavy vehicles to operate at their limiting or crawling speeds for the given terrain. So level terrain, basically, you have grades that are so mild that doesn't affect the traffic speed of heavy vehicles. Rolling terrain, you have an effect, can be affected substantially, but it doesn't force the tracks to travel at the crawling speed. Going back to the passenger car equivalent, PT or PCE, that equivalency factor is a function of the terrain. So basically for level terrain, the factor we're going to be using is 2. So we're saying that one track is equivalent to 2 passenger cars. And for rolling terrain, we're saying that one track is equivalent to 3 passenger cars. And that's it. You will pick a value, one of these two values from this table. Let me finish with this. When the analysis segment consists of terrain that cannot be considered as an extended free general segment, we have to use one of the tables that you have in your book, 6.6, 6.7, and 6.8. And notice that those tables depend, unlike the previous table that didn't account for when we have single unit tracks or tractor trailers, these tables are different depending on the proportions of single unit tracks and tractor trailers. So if your total truck traffic consists of 30% single unit tracks and 70% tractor trailers, you will use table 6.6. If it's 50-50 the split, you will use 6.7. And it's 70-30, you will use 6.8. The type of tracks now, it's important for extended freeway segments, is not for the extended freeway segment procedure. And the table, this is an excerpt from one of the tables, table 6.6, they look like this. You have the grade, it's one of the inputs. The other input is how long the grade is. And then the other input that is important is percentage of heavy vehicles in the traffic stream. And then you read, entering with these 3 inputs, you will read one value corresponding, let's say, for 2% grade, that is 0.625 miles long, and with 10% tracks, I would pick the value, the passenger car equivalent of 2.50. So since I ran out of time, let's continue with this next class. So let me refresh what we were discussing. For the highway capacity analysis, we need some geometric data, either the field measure free flow speed or the base free flow speed, some volume information. And we have to compute 2 things. And these are the 2 branches of this diagram. One was computing the free flow speed. And we did that with some adjustment factors for lane width, lateral clearance, and that was a function of the number of lanes, and also something else with interchange density. We will refresh this again when we look at the problem. And then we move into the other branch, which is the volume adjustment factors. We started talking about this. We said, well, we get a given volume, total in all lanes, and that's in vehicles per hour, and we need to adjust that for a peak hour factor, number of lanes, and heavy vehicles. So I will show you this. So we said we get this volume, and we'll adjust this for the peak hour factor. That, just to refresh your memory, is something to account for the fact that the demand is not uniform during the hour, so we account those traffic fluctuations, random fluctuations we have during the hour. So this peak hour factor, we're making analysis accounting for the most congested 50-minute period. We divide by the number of lanes to convert the volume in vehicles per hour, total in all lanes on a per lane basis. And then finally, we started talking about this heavy vehicle adjustment factor to account for the fact that not all vehicles in our traffic stream are the same. You can see that in general, truck traffic occupies more space, and also it has lower performance. So we discussed those things the other day, and this is more or less where we finished. We started talking about this the other day. We said we are going to compute a heavy vehicle adjustment factor, which is a function of two things: the percentage or proportion of tracks in the traffic stream and passenger car equivalent. So this term tells us each track is equivalent to how many cars in the traffic stream. So we're going to convert a certain volume of vehicles that include tracks into equivalent volume of passenger cars. So obviously you need more cars to replace the tracks and have the same performance characteristics. So basically that's more or less where we stopped the other day. I went a little bit further just to say, well, when we got to this point, I need to tell you that the highway capacity manual considers two different types of segments. They call one extended freeway segments and the other one specific grades. Basically, the specific grades is when the performance of a track suffers significantly because of the combination of the grade and the length of the grade. So whenever that's not the case, we will use extended freeway segments. For extended freeway segments, we will have to define our terrain either as level or rolling terrain. The difference between these things, you have here a general classification of what it means. Sometimes clear cut that something's pretty level, sometimes clear cut that something looks more rolling. Most of the time, or a lot of times, the division between the two is kind of fuzzy. So in this class, I will tell you it's either level or rolling terrain, but in practice, this is a decision that someone has to make what type of terrain you have. That definition is that essentially your passenger car equivalents depend on the type of terrain you use. So for level terrain, we said a track is going to be equivalent to 2 passenger cars. For rolling terrain, 1 track is equivalent to 3 passenger cars. And notice that we're not talking even about the type of track. We just say a track. It doesn't matter whether it's a single unit track or a tractor trailer track. And you can see those tracks are not the same, but for this type of analysis, since it doesn't affect much the speed, that's a highway capacity manual data, right? So it tells you to do either 2 or 3. Those are the factors you use. And that's given in table 6.5. When you have specific grades, then you have different tables to figure out what the passenger car equivalents are. So sometimes you're going to see I call it PCE, or sometimes I will be calling it ET. So now you have 3 tables in your textbook. Table 6.6, 6.7, and 6.8 that depend on the percentages of single unit tracks and total tracks relative to the total percentage of tracks. If 30% of them are single unit tracks and 70% of them are tractor trailers, then you use table 6.6. If they are divided 50-50, then you use table 6.7. If you have 70% single unit tracks and 30% tractor trailers, you use table 6.8. And obviously, the real world never comes 30-70, 50-50, or 70-30. You will have to find the conditions that are closer to one of these tables. I put in the notes excerpts from table 6.6, and the next slide is for table 6.7. These values that you see in the middle of the table are the passenger car equivalents, and they're a function of the grade of the road, the length of the road, and the percentage of heavy vehicles you have. So this is when we have 30% single unit tracks and 70% tractor trailer tracks. This is the other table when we have 50 and 50, and there's another one with 70 and 30. I chose here these values because I want to use them later in a problem, so I put higher grades just to indicate that the values continue down. Notice that the first one starts with 0, 2, 2.5, then it goes to 3, 3.5, 4, and then it goes to higher values, right? So for the second table, I put 4.5, 5.5, and 6. And then you have variable lengths and the percentage of tracks, same thing. So something that is interesting here, let's say we choose a grade of 5.5%, and let's say that the length of that grade is equal to almost a mile, 0.875 miles. And let's say we have percent of heavy vehicles in my traffic stream is 10% tracks. Since I'm having 50% single unit tracks, of all the tracks, 50% are single unit tracks and 50% are tractor trailer, that means that I have 5% of my total traffic stream corresponds to single unit tracks, and the other 5% corresponds to tractor trailer tracks. So with that information, all we need to do in this type of tables is just say, okay, this is my passenger car equivalent. Each track is equivalent to almost 4 passenger cars. So is that as simple as picking this value here and that value there. The variations of the values make quite a bit of sense. You can see that for one length, let's say 0.875, let's say for that length, I pick a passenger car equivalent for, let's say, 2% tracks. So for 4.5% grade is 832, but when I go to a 5.5% grade, it's 937, it went up. If I pick one for 6% grade, it's 11.78. You see, as the grade increases, one track is equivalent to more passenger cars. That means you need a higher volume of passenger cars to get to conditions that are equivalent to the original traffic. Because one track on a steep grade will slow down significantly. So in order to replicate those conditions with just cars, you have to put a lot of cars. You can see it makes sense. The grade increases and your passenger car equivalent increases. The other thing that you may notice is that for a given grade, let's take the 5.5% grade, again, as you increase the length of the grade, the passenger car equivalents increase. That also makes sense because if I have a 5.5% grade and the length is very short, the track is not going to reduce the speed that much. But as I make the grade longer, at some point you want to reach a crawl speed. And so it has a higher chance of affecting more and more vehicles as they go up the grade. So that's why you see the passenger car equivalents increasing with the length of the grade. Now, the other thing that's interesting is that as you increase the number of tracks or the percentage of heavy vehicles in the traffic stream, you can see that the values, if I pick one set of conditions here, the values decrease. Does that make sense? It makes sense too. You know, you put one track, and that track, like I mentioned before, if it's a long grade, it will affect a lot of cars. Now, you put a second track, it has the potential to affect the same number of cars. So let's say we put the second track in front of the first one. Since the first one is already affecting some vehicles, those vehicles don't reach the second track. So the effect of the second track becomes smaller. And as I keep doing that, essentially you end up with platoons of tracks affecting fewer and fewer cars. So the fact that these values decrease in this way also makes a lot of sense. All these numbers have been derived from simulation, traffic simulation studies with performance of tracks and things like that. Some of the things we have been discussing before in the class. But I want to give you some intuition of why you pick a value and the value makes kind of sense. So there are some other details that I'm not going to discuss. You know, you can analyze a single grade, but most of the time you don't have a single grade. You have combinations of grades. We're not going to care about those details. The last thing I want to talk before we go into the problems is we were given this expression. Your textbook, it just gives you the expression and it tells you this, how you convert percentage of tracks and that number of passenger car equivalents into something that they call a heavy vehicle adjustment factor. I just want to show you where it comes from. Let me just give you an example. Let's say we have 2% tracks. That means that for every 100 vehicles, 2 of them are tracks. So let me put here 2%. Most of the time, I could be talking about proportion, 0.02. And right now, I want to put it in percentage because I want to make it for 100 vehicles or to make it more intuitive. Let's say for rolling terrain, we said the passenger car equivalent is 3. If I multiply 2 times 3, that tells me that that's equivalent to 6 passenger cars. If I have 2% heavy vehicles, that means that 98% are cars. So I have 98 cars. For 100 vehicles, I have 98 cars and 2 tracks that are equivalent to 6 passenger cars. So if I add those two, I get 104 passenger cars. So if I have an original volume of 100, so I have 100 vehicles, which is equal to 98 passenger cars. This is in passenger cars, and this is in tracks. We're saying we need a higher number of cars to have the same performance as the original traffic that had 98 cars, passenger cars, and 2 tracks. So the point is that my original quantity, I'm going to increase it to convert it into passenger cars. So we need something that is greater than 100. Or if I work in proportions instead of percentages like I just did, I will need a value greater than 1. Right? And that's what the heavy vehicle adjustment factor does. Why they chose to divide by that adjustment factor. My guess is that they decided to divide by a number instead of multiplying by a number, just because the peak hour factor is divided, the number of lanes divided. So just to make it consistent, they decide to divide by another factor less than 1. But basically what we are doing here is we are saying that this has to be equal to a value greater than 1. Instead of making that value greater than 1, I want to make 1 divided by a value that is less than 1. That's what they define as the heavy vehicle adjustment.
How did you find that ET was 3 for the example you just did?
So the previous discussion was all about what values we get. So if I'm talking about level terrain, that's my ET. If it's rolling terrain, that's what I said, let's assume it's rolling, I have a passenger car equivalent of 3. If I'm doing a specific grade analysis, it will be one of the values in one of these tables. Let's say something like that, or it could be 10, or it could be 12. It depends on how steep the grade is, how long it is, and the percentage of heavy vehicles I have in the traffic stream. So that's how you get the passenger car equivalence. Once you have that, we come into this equation, and essentially we're going to convert a certain volume of passenger cars into a value. We're going to multiply it, or that volume we're going to divide by that heavy vehicle adjustment factor, which is a factor that is less than 1. So essentially when you divide by a factor less than 1, essentially it's like multiplying by a factor greater than 1, which is what I was trying to explain with this equation. So I just showed you that this 1 over FHP has to be greater than 1. That was the whole point of the conversation. Now, just to show you that this equation that you see here is equivalent to this one, let me just do 2 small modifications to the equation. The first one is recognizing that is what I did earlier, right? If here I put 98 and here I put 2, they add up to 100, right? So, or if I work in proportions, they add up to 1. So that's what I'm putting here. I'm working in proportion. I'm saying, well, the proportion of cars is 1 minus the proportion of trucks. So this equation is the same as this one. And then you can work with this equation because it's essentially 1 plus PT multiplying ET minus 1. So I can rearrange that equation like this. And now you see that if I solve for HP, I get that equation here. Solving for this, we get that equation there. So this slide is essentially proving that where this equation comes from, and the concept is just the concept of equivalency. You are converting traffic in vehicles that consist of passenger cars and trucks into passenger car equivalents. And notice that here I'm clarifying that in this equation I'm working in proportion, but I can get the same result if I put here 100 and in here I plug a percentage. Okay, either way it works fine. And of course, obviously here I also have to put 100. So with that, basically we cover this equation, and then the last thing that we need to do is here we have 4 steps, but it's really very simple what we have to do. Once you compute the free flow speed and you compute the flow rate, the next step is to define the speed flow curve. Basically, it's looking at this diagram. With the free flow speed, if it's 75, we'll pick this curve. If it's 70, we'll pick this curve. If 65, we'll pick this curve. If it's 67.5, we will draw a curve that is in between, interpolating and so on. That's the first step that you see here. Determine the speed using the speed flow curve. Basically, what that is saying, once we know the volume, let's pick 2000, an easy value for me. And let's say we're working with the 70 miles per hour speed flow curve. That means that if I move up, that's slightly less than 60. You guys can see that that point, it's almost 60. Okay, so that's what it means here. Determine the speed flow, the speed using the speed flow curve. Then it says compute the density using the flow rate and speed. That's nothing more than We take the flow rate, that is a value that we already determined, and we divide by the speed we just determined in the previous step, and that gives us a density. And finally, we have here, it says determine the level of service, which is nothing more than either looking at the value of the density and looking at the table for densities, figure out where it is, or just simply based on the noticing that that point falls in between these two lines, and that corresponds to level of service D, you can say, oh, that's level of service D. Or with the value of density that you determine, you notice that that falls between 26 and 35, and those two values correspond to level of service D, the thresholds for level of service D, and again, you define level of service D. So you can do it with the chart or with the numbers. In the class, I'm going to ask you to do it with the numbers because I can check things more easily, but either way is fine in practice, right? So these are the values that I mentioned. These are the thresholds. This is the maximum for level of service A, the maximum for level of service B, the maximum for level of service C. And notice that that doesn't change with the free flow speed, with which curve you're using. And that's one of the advantages of determining the numeric values. It doesn't matter what your free flow speed is. Once you figure out the density, you know your level of service. The other performance measures that you have here that we said the other day are equivalent only for that free flow speed. So if you have a free flow speed that's in between two values, you cannot look at these values other than the density. The density is the only one that will tell you exactly what level of service you are. Okay, so let's look at an example. So this is a typical problem, and this is an example in your textbook. A 6-lane urban freeway, and this is typical. Typical, you will, in practice, you will hear someone will tell you, oh, we have, this is a 6-lane freeway. That means 3 lanes in each direction, okay? So if I tell you in a problem, a 6-lane urban freeway, and I forget to tell you it's 3 lanes in each direction, that's the assumption you have to make, okay? So you have 3 lanes in each direction. Typically, I try to clarify it so you don't get confused because not everybody is familiar with the language that transportation engineers use, but that would be a typical case. So it would be the 4-lane freeway, 6-lane freeway, 8-lane freeway, 10-lane freeway. So those would be the case. So a 6-lane urban freeway is on level terrain with 11-foot lanes, obstructions 2 feet from the right edge of a traveled pavement, and 9 ramps within 3 miles upstream and 3 miles downstream of the midpoint of the analysis segment. A directional weekday peak hour volume of 3,000 vehicles is observed, with 810 vehicles arriving in the most congested 15-minute period. If a traffic stream has 10% single unit tracks and 10% tractor-trailer tracks, determine the level of service. As usual, a lot of these problems are very verbose, and one of the things you have to do is distill the information that is given to you. Okay. So let's look at how we solve the problem. I have tried to help myself with arrows and things, so and also it makes, I think it makes it easy for you to when you review this. Although now with the videos probably it's easier. And I have put here the problem statement once again, and I have highlighted some of the basic information that is given. Not all, but some of it is highlighted. So remember, we have some basic information at the top of the chart, and that information is given in the problem here, and then we have to compute the free flow speed and the flow rate. So let's start determining the free flow speed first. We don't have anything measured about free flow speed, so we're going to use the high capacity mine. And so in that case, you have to remember this equation is given. You can have it in your cheat sheet. Actually, you will have it, it's open book, so you will have it in your notes. So the free flow speed is equal to the base free flow speed, which is always 75.4, and we're going to adjust that for the lane width, the right lane width, and lateral clearance, and the total ramp density. Okay, so let's look at the lane width. For us, it was given as 11-foot lanes, right? So that was given to us. So if we look at 11-foot lanes, we get the value of 1.9 miles per hour. So it's something that we subtract from a speed, so it has to have units of speed. So that's the factor for right lateral clearance. So that's easy, right? Right. Cannot give you anything more trivial than that in this class. Then we have to adjust for lateral clearance. And remember, lateral clearance depends on the right shoulder lateral clearance and depends on the number of lanes we have per direction. So in this problem, we have lateral clearance of, I thought I had highlighted this here, but we have 2 feet from the right? So that's why I entered here with 2 feet. And also we have 3 lanes in each direction, and that's why we enter with on this column. So this column and that row, that gives me an adjustment factor of 1.6 miles per hour for the lateral clearance. For the right lateral clearance. And finally, we need to figure out that ramp density, and then you have to look, okay, what information I'm being told about ramps. So even though we're talking about freeway segment, supposedly we don't have ramps. So we're analyzing a segment without ramps, but there are ramps close by, and those ramps, they kind of affect the overall flow performance. That's why we consider this. So in here, we were told we have 9 ramps within 3 miles upstream and downstream of the midpoint of the analysis segment. So that means that essentially we have 9 ramps in 6 miles. So that's a total ramp density of 1.5 ramps per mile. And with that, we have everything we need to compute the free flow speed, 75.4 minus the 1.9 minus the 1.6 and minus 322 times the total ramp density, which is 1.5 raised to the 0.84 exponent. So if I plug in values, I get 67.4. And this would be obviously, I don't know why I didn't do it, but I should have put this in vehicles per month and miles per hour, sorry. Miles per hour. Okay. Any questions so far?
No.
I hope you guys agree with me. It's really, really straightforward. Okay. It's basically putting values into equations, that's it. And well, here I had the units after all. So that's our free flow speed. The next thing we need to determine is the flow rate, right? So for the flow rate, we need to use our equation. We need to take the volume divided by the peak hour factor, the number of lanes, and the heavy vehicle adjustment factor. Remember, the peak hour factor is the volume divided by the maximum flow rate within the hour. And let's look at where that information is given. Well, some of the information that's relevant to this part of the problem, we have 3 lanes in each direction. That will be the n will be equal to 3. We were told that we have a directional, so it's already given in our direction. Typically, many times the volume, the total volume will be given to you in both directions. In that case, you have to divide first by 2. But since it was given directional, in this case, we have 3,000 vehicles in an hour. That's the peak hour volume. With 810 vehicles arriving in the most congested 15-minute period. So notice that in this case, they're not giving you the peak hour factor. They're telling us, oh, we have 3,000 vehicles in an hour, but in a period within the hour of 15 minutes, I had 810 vehicles counted in that 15-minute period. And that was the maximum of any 15-minute periods within that hour. Okay? And also, we're also told that in our traffic stream, we have 10% single unit trucks and 10% tractor trailer trucks. So that means of all the vehicles I have in my traffic stream, 20% of them were trucks. Okay? And with that, we need to determine that level of service. So now we can use our peak hour factor equation. It's simply V is the 3,000 vehicles per hour. Okay? And then that information here is what we call the other day BT, which is the number of vehicles counted in the most congested 15-minute period So it's basically a volume, but it's a volume on a 15-minute period. And then we multiply that by 4 because we have 4 50-minute periods per hour, right? So this denominator, when I make that multiplication, you can see that if I had this flow rate, if I have this rate of flow of 810, in every 15-minute period, my volume would have been 3,240. My actual volume is 3,000. But because of the variation in the most congested 15-minute period, traffic during those 15-minute periods are flowing at an equivalent rate expressed as an hourly basis of 3,240. And then the ratio of these two things is 0.926. That's the peak hour factor. Remember, if we divide this by the volume by that value, we would be considering the traffic as if it were running at, it would be equivalent to the most 15-minute congested period during the hour. Okay, so it's just a matter of plugging in values in here. So we have the peak hour factor, number of lanes, I will put it somewhere over here, is equal to 3, we already mentioned that, and then we need to figure out the heavy vehicle adjustment factor, and for this problem, I'm going to look at this table because we are told that we have somewhere over here, is on level terrain. I forgot to highlight that one. It's a 6-zone freeway, is on level terrain. So because I'm on level terrain, I have to look, it's an extended freeway segment, and then I will pick this value for the passenger car equivalent. Okay. So I'll pick that value, and that corresponds to level terrain. And then I have 10% single unit tracks and 10% tractor trailer tracks. And that basically tells me, oh, I have 20% tracks, so my proportion of tracks is equal to 0.2. And then the other input that I'm putting here is the passenger car equivalent. And so I apply my equation for heavy vehicle adjustment factors, and I get a factor of 0.833. And together with the number of lanes, and okay, so with the number of lanes, I can already apply everything into this equation. I will come back to this in a second. I don't want to, okay, so here I have it. I will come back to this in a second. So with that, heavy vehicle adjustment factor, number of lanes, and peak hour factor is just a matter of plugging those values into this equation together with the 3,000. And we get a flow rate of 1,297 passenger cars per hour per lane. Notice that we're not talking about anymore about vehicles per hour. So this value here was given in vehicles per hour for all lanes. Okay. The fact that we have divided by 3, we have converted that into on a per lane basis. We divide by 3, we convert into from vehicles per hour to vehicles per hour per lane. And dividing by this factor, which essentially makes the conversion from passenger cars, from tracks to, from a mix of cars, passenger cars and tracks into just passenger cars, we convert this from vehicles per hour per lane to passenger cars per hour per lane. Okay. And finally, this other factor accounts for the peakiness of demand, for the non-uniformity of the demand. So with that, we get this value. And if you remember the equations the other day, and you have it, you can go back to your notes. The equation for the float, which is a horizontal line up to a point and then it starts a quadratic. So the transition from a horizontal line to the quadratic is what we call the flow rate corresponds to that. It's called a breakpoint flow rate. There's an equation in the high capacity manual. It's this one, 1,000 plus 40 times 75 minus the free flow speed. So it's a matter of plugging the value of the free flow speed, which we derive as 67.4 before. So we get that breakpoint is 1,304 passenger cars per hour per lane. And we will see the relevance of that value in a second. Okay. So now we can determine basically our level of service. So we have the flow rate, and the free flow speed was 67.4. So we can do two things, 1297. We can first recognize, if we try to do things numerically, recognize that our flow rate 1,297 passenger cars per hour per lane is less than the breakpoint, which is 1,304. It's slightly smaller, right? So that means that whatever my curve is, let's take something like this, our point, our flow rate is to the right of the breakpoint. So that means that the speed will be equal to the free flow speed of 67.4. Okay. Also, you can look at that from the figure, but in order to do that, what you will need to do is, what I did here is to interpolate for 67.4 miles per hour. I draw the line, right? And then I enter my graph with 1,297. In order to do this, you need to really pick things in a scale. So, and in a test, you cannot do that. So that's why I always prefer, let's work with the numerical values. There's nothing wrong with doing things graphically, but then I get 30 different answers, and also I like to know what you guys are thinking. So that's the only reason why I'm saying we're not going to do it graphically, but it's as simple as that. And so here we're saying, oh, the breakpoint is somewhere over here, seems to be somewhere over there, and we just are on the right. Actually, it should be even closer to somewhere over there. Okay, that's the breakpoint. And since in this case we get something smaller than the breakpoint, we have a constant. We are on the flat portion, so that's the speed. Okay. Now, once I figure out the speed and I know the flow rate, the ratio of the flow rate to the speed gives me density. Okay. So 1,297 divided by 67.4. This is in passenger cars per hour per lane, and this is in miles per hour. The hours cancel. I end up with passenger cars per mile per lane is 19.2. And you can see 19.2 falls between 18 and 26. And if you go back and look at the tables in your textbook, that corresponds to values of level of service C. So once you get this value here, you can tell me, since those values are between 18 and 26, you have a level of service C. You can also just look at this point and you see, oh, that falls in the level of service C section. But for that, you need to make sure that your points, everything is, you're entering values up to scale and precisely. Any questions? Because this is the analysis, the heavy capacity analysis. It's that simple.
What if S is not equal to FFS?
Okay, we'll see that in the next example. So let's do that right now. Let's answer that in the next example. The next example is basically, I'm giving you information. Let's go ahead. We have conditions in the previous example. You can see this one. At some point further the roadway, the 6% upgrade is 0.25 miles long. So we don't have levels anymore. By this significant grade. If I tell you it's the rain, that's essentially, and I give you a grade and how long the grade is, you have to use the extended freeway segment or the specific grade segment analysis. And that's the only change with the previous problem. All other characteristics are the same as before. So again, we're asked, what is the level of service of this portion of the roadway, and how many vehicles can be added before the roadway reaches capacity? So part of the problem is the same as before. We need to determine the level of service, but we're asked another question is, how many vehicles can we add until we get to the capacity of the road? So let's try to answer these things. Okay. You're going to see the first part of the problem is basically the same. So I cut and paste the things. So I have the same free flow speed. The things that we did here, they are still valid. We still have 11-foot lane, so the lane width factor is the same. The lateral clearance factor, we still have the same things. We still have 3 lanes, and we still have 2 feet lateral clearance. The ramp density is still the same. So this part is all the same. We still get 67.4 miles per hour, our free flow speed. Okay, so far, no change. Now, the second part starts changing a little bit. So we use the same equation for the determination of the flow rate. We still have 3,000 vehicles per hour. We still have 810 vehicles arriving in the most congested 15-minute period. And so the peak hour factor is exactly the same as in the previous problem. We still have 3 lanes, right? So that doesn't change either. But now the passenger car equivalents change. This is different. So my passenger car equivalents, now I have to look at 2 things. One is going to be which table I'm using. So I'll be back in a second about which table we use. And the other thing is that when we use the equation for the heavy vehicle adjustment factor, remember we have to enter the percentage of tracks. So, and this is the same as I did before. We have 10% single unit tracks and 10% tractor trailer tracks. It means we have 20% tracks in the traffic stream. So I'm using the 0.2. I'm still using this 0.2. But now, and I look at the notes a little bit earlier, I should have put an arrow this pointing to this table with this information, because this information I'm also using to select which table I'm going to use. If you go back into your textbook, table 6.5, I think 6.5 is used for, well, I don't remember if it's 6.5, 6.6, 6.7, or 6.6, 6.7, 6.8, but the one in the middle corresponds to 50% single unit tracks and 50% tractor trailer tracks. Okay, so I pick the table corresponding to 50-50 because, you know, it's, if I have of a total truck traffic, because these 2 numbers are the same, it's 50-50. Is that clear? So this 10% is as a percentage of the total traffic stream, including cars and different type of tracks. This percentage is of all the tracks, what percentage are single unit tracks and what percentage are tractor trailers. Is that clear?
Yeah, I think that's clear.
Yeah, because I could have given you, oh, I have 3% here and 6% there. That correspond to, or sorry, 3 and 7. That means that would be 30-70, right? So I can pick values that are different values from this, and you will have to select this table. So that's part of your job, right? So finding out which table you have to use. So that's why I picked the table corresponding to 50-50. That's an important thing that I don't think I put in the notes. Okay, so make a note, or when you look at the video again, just remember that that's important. Don't pick a table out of the blue. You have to select the table based on the information that is given to you. And then we have to look at, okay, we have a 6% upgrade and it's 1.25 miles long. So that's why I picked 6% and a length of greater than 1. So unfortunately, I crossed it out there, but you see the last value is for a length that is greater than 1. I'm pointing out here, or here. If you look at the previous grade, you can see that it's greater or equal than 1. Actually, what I could do is just take that line. You can see it's greater or equal than 1. Okay, and that's why with 6%, greater than 10, and with 20% tracks, again coming from there, we come up with this value, which is going to be our value of passenger car equivalence for this problem, 3.27. So you can see it's significantly higher than the 2 that we used in the previous problem, and that's related to the terrain. And so with that, now we can use our passenger car equivalent and the percentage of tracks, or the proportion of tracks, to figure out the heavy vehicle adjustment factor. Before we had 0.833, now it's 0.688, so it's a much lower value. That means that we will be converting our volume into a much higher number now, because we're dividing by this factor. So if we use the n equal 3, we can compute our new flow rate. And now we see that we get 1,570. Before, I think, if I remember correctly, it was 1,297. So it's a higher value, even though the rest of the problem is almost identical. Okay, so that's the value for the flow rate. And now we have the flow rate, we have the free flow speed, we can compute the level of service very easily. So similar to what we did before, we determined the breakpoint. The breakpoint is exactly the same that we did before. It's a function of the free flow speed. And in this case, our flow rate is higher than the breakpoint. And now to answer the question, I don't remember who asked. I think, well, I don't know who asked the question, but the question was, well, what if our flow rate falls in the bending portion of the curve? If that's the case, we need to compute the capacity, which that's a function also of the free flow speed. Again, that's an equation that is given in these notes. Remember, it's the minimum of 2200 plus 10 times the free flow speed minus 50, or the value of 2400. So in this case, if you plug your free flow speed, 67.4, and compute this quantity, ends up being 2374. And since that value is less than 2400, that's the value that you select. If the value had been 2450, you would have selected 2400. Okay, so this is the capacity of the road, and then there's an equation that is basically the free flow speed minus the free flow speed minus the capacity divided by 45, multiplying the VP, which is the 1570, minus the breakpoint square divided by the capacity minus the breakpoint square. Again, it's an equation that you have to go back in the notes and look at it. It's given, you will have it. So it's just a matter of plugging in values. We are plugging this value here, you're plugging these values over here, and these two values over there, okay, and that one. So it's just a matter of plugging in values. You have the equation in your notes. So in this case, instead of 67.4, like we had before, now we get 66.5 for the speed of traffic. So to finish the problem, basically, or the level of service determination, we just compute the ratio of the flow rate to that speed is 23.6. And again, you have to compare with the thresholds for the level of service. And we find that that value, even though it's higher than what we had before, still falls between 18 and 26. So we're still at level of service C. And that answers the first part of the question. As usual, you could have done this graphically. You select your value of the flow rate, and also you interpolate, in this case, for that the 67.4 free flow speed. So that blue line corresponds to that, an interpolation for that speed. I did the best I could by interpolating there. And then you enter, and you can see that value will give me the what speed I'm working on. And this point, it's already telling me, oh, that corresponds to level of service C. Okay? And that's it. Notice that before we had a point over here, it was level of service C. Now we have a point over here, it's still level of service C, but if you increase the grade a little bit so that the passenger car equivalents are a little bit higher, or the proportion of tracks, you change some things, it can put you here. So it can drop to levels to a different level of service. And you don't know until you do these calculations, right? So in this case, we're still at level of service C, but a little bit more traffic that we add, we will drop one level of service. Okay. Any questions for this part? Let me answer very quickly then the last part, which it asks how many vehicles can be added before capacity is reached. So to answer this, we need to determine the hourly volume for capacity conditions. So if we determine the hourly volume for capacity conditions minus what the volume that we have, essentially that tells us how many vehicles we can add before we reach capacity. Okay? So, and let's remember, for this problem, the capacity is a function of a speed. So that gives you this value of 2374. We're using that value for the capacity. And so if we make our flow rate equal to the capacity, okay, assuming everything else is fixed, which is, you're going to see some of those assumptions are not that strong, they're not that reasonable. So assuming everything else is fixed, you can put use the same peak hour factor, the same heavy vehicle adjustment factor, the same number of lanes, and then you can solve for what volume would correspond to capacity conditions. Okay? So if we solve for that volume, we get 4,537. And basically the difference between that volume and the volume of 3,000 that we originally had is how many vehicles you can add before you reach capacity. Okay, so that's a variation of the type of problems that I could give you, but I don't like this one that much. But now, I said some of the assumptions are not that realistic. First, I have written here that the assumption about the peak hour factor is not realistic. The higher you get, the higher the capacity, the closer you get to capacity, the variations in flow become, the variations in the demand become smaller. So the demand becomes typically more uniform. So it's unlikely that the peak hour factor will stay at the value that you have. Okay, so that's one of the problems with this. The other assumption is that you are assuming that the traffic conditions are not going to change. For example, truck drivers may have very good information and may decide, well, I'm not going to travel at the peak hour. I'm going to go at some other time because it will be a waste of time to be traveling at that time of the day. So the percentage of trucks may change, and that will change your heavy vehicle adjustment factor. So there are things like that. So these things are not perfect. And because of some of the things, you see why there's not much point when you give the final answers in this type of problems in practice, giving things with decimals. So in practice, you will not be working with decimals. In this class, I will ask you to round to the nearest vehicle just for easy of grading, but that's it. Okay, so any questions before we move on? This is basically the type of problems we're going to cover with this subject. They are very simple. So whenever I add this in the final, I think it plays to your advantage because there's no much room to get things wrong if you pay attention. Just plugging and checking values, that's it. Any questions about this before I move on to the last thing I want to cover about this? Okay. Oh man, we're getting to the end of the semester where people are losing interest. 20 people still participating. Yeah. Okay. No questions? I have 5 in the chat. Let's see. Yes, I understand. Yes, no. Okay, so nothing. Okay, who wrote no? I don't know the no answer to which question was that, but okay, so I don't hear anything, so let me move on. Let's talk about one last thing about this. And it's not that we are talking about a volume, but the thing is with traffic is, we're not dealing with a quantity that is deterministic. It fluctuates, right? So, and that's why I want you to read the last section of the textbook just to give you an idea of, I'm not going to test you on this, but when you learn a subject, try to learn it well. Traffic has a lot of variation. So there's variability in the traffic volume by time of day of week, time of year, and type of roadway. There's also temporal variability in traffic flow, right? So some of it, we're accounting for it. We say, well, we have a volume over an hour, but we are considering the variation in 15-minute period. So even within the hour, it's changing. But these are figures that I recreated from your textbook. And basically, here your textbook is showing you there that, hey, during the day, traffic is changing, right? So at close to 5 p.m. is the lowest. Then we have a peak at around 8, it seems here is around 8 a.m. And then we have another peak in the afternoon. Okay, so this is for a typical weekday, and the other one is for a typical weekend day. And so, and here you have another example where they have a single peak. So it depends whether you are in so these are for intra-city, so this is something like Honolulu, and this will be an intercity route when you're traveling between two population centers. So the peak, the characteristics are different depending on type of road you're dealing with. But the point is that, and it's not clear in that figure how what do they mean by percent of daily traffic? I imagine this is on an hourly basis, so it's like 2%. At this time of the day, we have only 2% of the total day traffic. Okay, so but the point is that you have higher traffic in some time of the day and lower traffic in other time of the day. So it varies during the day. The same thing if I look at it in terms of monthly. So if I look at the monthly data, and now here we have a different scale. Here we said, well, over the year, if I count all the vehicles that cross that point and I divide by 365 days in the year, I will get my traffic expressed in vehicles per day, and that's what we defined before as the annual average daily traffic. So that's an average over the whole year. Now, in the month of July, on average, the traffic per day is much higher, and that's why you see it's about 40% higher than the ADT. And in the month of February, it's for this line, let's say, it's around close to 70% for recreational highways. For business routes, it's a lot more uniform. But still, you have variation from winter to summer. Okay? So with that said, we have variations that are daily, we have variations that are hourly. For the hourlies, we accounted already. And we have variations that are monthly variations. So when we select the design hour volume, what volume should we design? It's not an easy question, right? So that's when, when people are confronted with these things, they come up with rules. In highway engineering, what has typically been done is different highway departments will do different things, but typically they look at this, they put at the hourly volume, and they rank them. So what this graph is saying, and this again is a graph taken from your textbook, you're going to order your hours of the year. So you create let's say, kind of a bar graph. This would be the first hour, and then you put the volume corresponding to the second hour, the volume corresponding to the third hour, and so on. And by first hour, second hour, and third hour, what I mean is the hour with the highest volume, then I have the hour with the next bar corresponds to the hour with the second highest volume, and then the hour with the third highest volume, and so on. And if I join the middle points of those bars, I will get a graph that looks like this. Okay? So the only difference that in this graph, in terms of expressing the volume, I'm expressing that as a proportion of the annual average daily traffic. So remember, the daily traffic is expressed in vehicles per day, and this volume is in vehicles per hour. So it's the volume is much lower than the daily traffic, right? That's why you get a proportion of about 0.15. Don't ask me why the people did this way, but that's how they do. So you order the things in that way, and then for design, typically, there have been economic studies, what would be the proper values to use, but for design, people have chosen between the 10th and the 50th hour, and typically the 30th hour is chosen. So this is what it says here. The 30th highest hour is chosen for design. Okay. So what that means is that if you create a graph like this, you just pick the 30th hour and you say, okay, I'm going to design that for whatever volume corresponds to that value. That's going to be my design hour volume. And the way you pick this up, since this expressed as a function of AEDT, don't worry, it's written later, but and this is my design hour volume. Typically, that's defined as a value of K, which is what we're putting here in this axis. So if you have this information you typically have, and once you select a K value, this is something that someone will do for research. In an area, someone will say, okay, for our area, we use a K value of 0.12, so you multiply that by your AEDT, and that's how you get your design hour volume. Okay, so I'm just trying to tell you how these values actually, how that B that of 3,000 that we told you in that problem come about. Okay, so you have that equation there in the notes, and in the next note it's basically the same, but also most of the time the AEDT will be given in both directions. In that case, you have to multiply by the directional factor. But that's it. With that, you will get the design hour volume for design. I'm not going to test you on this last part, but I just want you to know that those values don't come out of the blue. Typically, there would be some research study, and over time there have been debates what's the right hour to use. You don't want to use a value that is too high because otherwise you are over designing the highway. But if you pick a value that is too low, it will result in a cheaper design, but you will have a lot of congestion throughout the year. So a lot of these things end up being kind of compromises in between. Okay, so that's it for highway capacity. For once, I want to finish 5 minutes earlier. That's for the additional minutes I took the other classes. Next class, I'm going to start with signals there.